Hello everyone, this is Ashok of Department of Computer Science and Technology, and coming to the second video of design and analysis of algorithms, where we're going to discuss about design strategies. We've discussed about what is an algorithm and how you write an algorithm and what are the characteristics that are necessary for an algorithm, and we'll look into different design strategies of how you can strategize an algorithm or how you can design an algorithm, and we'll come to why efficiency is needed or why you need to analyze algorithms and essentials to calculate efficiency or essentials to calculate or essentials for analyzing an algorithm is what we'll look into. These are the contents for this video for today. Design strategies. There are various ways of representing or various ways of strategizing your algorithm or based on the kind of problems, definitely. So some of the majorly known design strategies are these are the various design strategies that most of us will come across while learning algorithms. And starting with divide and conquer. Divide and conquer is a strategy where you will divide the problem into sub problems and then you solve these sub problems and start solving the entire problem by solving these sub problems. And one of the major examples for divide and conquer are like quicksort, merge sort, binary search, and these are very familiar algorithms with respect to divide and conquer. And then there is greedy. Greedy is where, as the name suggests, greed, you try to get the maximum profit. Like if this is respect to optimization, so if you need profit, you try to get the maximum profit. So you get this maximum profit by calculating the local minima and assuming local minima is something where you make a best assume you assume or you make a best decision at a particular step, assuming that this step will lead to a global optimum, or sorry, small correction. Greedy algorithm is something where you make a decision or you calculate local optimum, assuming that it will lead to a global optimum. Consider a series of steps of choosing items. So you choose an item that best fits for you at every step, assuming that the overall items you chose will end up being your perfect fit. So that's something. And greedy, you have various types of algorithms in greedy, namely greedy generally involves various types of algorithms. With respect to minimum spanning tree, you can consider prims, Kruskal's, and DP, which is dynamic programming, where you break the problem into overlapping subproblems and avoiding repeated calculations or repeated function callings to reduce the number of operations or to reduce the number of function calls, in turn making a better efficient algorithm. So this is where you store the results, where memoization and tabulation are involved, which we'll discuss in further videos. And next, backtracking. Backtracking is something where you explore all possible solutions, but you backtrack when constraints are involved. So imagine you have a certain set of rules. You're trying to imagine a simple problem of uh, yeah, imagine a problem of solving a maze. You go in a direction assuming that it works for you until you reach the dead end. You reach the dead end, you backtrack or you come back to a next possible position where you can take another direction. So this is something that's similar to backtrack. And then randomization, as the name suggests, what it is. And then there is branch and bound. Branch and bound is something where you solve optimization problems by systematically exploring all the branches. We use state space tree, a tree like structure, to analyze or to find approximate solution. And branches, you analyze the branches systematically, and you explore all the branches systematically and bounding for suboptimal solutions. And these are the various design strategies that we'll come across, and why efficiency is needed. Or you can consider the next two topics as analysis of algorithms. So whenever we do a job, we tend to consider someone's job, someone's way of doing things, or someone's work as best if they do the job faster and with better quality. So, efficiency is needed, efficiency with respect to time, with respect to the resources used, but also providing similar or the best possible result. So, this is necessary for us to compare algorithms and to find or to get a best algorithm possible. So why analysis is required is to compare and find the best possible algorithm, and in doing so we have series of necessary essentials that are required to analyze a particular algorithm. First is line count. So imagine you have a simple code of imagine the same example that we have discussed in the previous video where we are trying to find a number in an array. So just an integer function which is find number, which takes an array, and target number. We try to calculate n, which is length of array, and then I'm just writing a rough pseudocode for this, rough code for this, and then you check, you initialize I, and you check while I is less than n. If a of I is equals to x, you return I, and if not, else I equals to I plus 1, and once you finish your while you have return minus 1. So imagine this simple code of finding a number where you take an array and a target element, and you find the length of the array, and then you initialize I0 while I less than n. If a of I is, if the element is found in it, then you return the position of the element. If not, you increment, and if the element is not found, you return minus 1. So in this the lines that are executable, in this the lines that are executable are the lines that come under line count, and operation count is where you have a certain operations that are being performed. This update will only consider as an operation when the condition is not satisfied. So except for this, the other operations will be counted for operation count, and these are line count and operation count, which are very basic topics coming to analysis of algorithms. The last simple topic that we'll address now is a posterior analysis and a priori analysis. As the names suggest, a priori and a posteriori. A priori is nothing but prior analysis, where you analyze the algorithm even before its implementation by mathematical calculations or uh, hypothesis, by using theoretical computations. And this is where algorithm design and logic comes are dependent. The tools we use are asymptotic notations and mathematics, which we will discuss in the following videos. The output of a priori analysis will be complexity of the classes, which is with respect to time and space, how efficiently your algorithm is using time and how efficiently it is using storage. Next, there is a posterior analysis, where you perform analysis of algorithms after the implementation, which is much easier, which is also an experimental evaluation, where the dependencies are the hardware requirements you have with respect to your CPU, RAM, and storage, the kind of compiler you're using, and the data you're giving to your algorithm. And the outputs are based on the kind of benchmarking tools or the metrics we are trying to use. You will end up getting the actual runtime that the algorithm took to run a particular algorithm, and also the amount of memory that it has used to do so. And that concludes the second part of design and analysis of algorithms.